So, as many of you know, I will be hopefully giving a talk at the International Space Elevator Consortium's annual conference in September for my ideas for a low Earth orbit space elevator extending 150 kilometers to 160 kilometers above Earth's surface, the largest single civil engineering project we've ever undertaken, a project which will sit at the confluence between civil engineering, aeronautical engineering, mechanical engineering, and space engineering, I suppose. So, yeah, a lot of different fields of engineering will have to form a confluence within this enormous project. It will be hugely expensive. However, it will allow us to do a great deal more in space. It may well open up Mars and the outer solar system for manned missions to space. It also serves the strategic interests of the West. Since China and Japan are thinking of building space elevators by 2050 and 2040 respectively, though they are reliant on the classical design of the space elevator, not the low Earth orbit space elevator, and they are planning on building these 36,000 kilometer long cables extending all the way to geostationary orbit, which is an incredibly long way away from Earth. And I don't think that their designs are as good as what I've developed. I don't think that a space elevator extending so far out to orbit, to geostationary orbit, for example, is a particularly useful machine. And I think that's what I'm going to start my lecture with. The criticism of other people's ideas, the criticism of space elevator designs from the past, what I would call the classical space elevator design. I don't think, because our fastest lifts at the moment, built by Hitachi, for example, go about 47, 48 kilometers per hour upwards. So going at those sorts of speed, a mere 47 kilometers an hour, that is really rather slow in terms of space travel. Spacecraft in space travel at something like 46, perhaps up to 67 or so thousand kilometers per hour, or 11 kilometers per second, or something like this. I don't know the exact figure off the top of my head, but it is in that sort of ballpark. Using an elevator going on a cable to geostationary orbit, that's really rather a sluggish way of getting around in space. What the low Earth orbit space elevator allows us to do is bypass rocket technology for getting into low Earth orbit, so about 150 kilometers up. And I believe it will likely provide a substantial cost-benefit saving over rocket launches and allow us to get payloads into orbit on a far more regular basis. And it will cost, yes, a lot of money in the first instance to get it operational. However, it will ultimately allow us to deliver a payload to low Earth orbit once every 4 hours or so. And we just simply can't do that with rockets at the moment. The turnaround time on rocket launches is weeks to months. They cost a very large amount of money to get payloads into orbit. The cheapest rocket we've ever developed, the Falcon 9 of SpaceX, that cost about $67 million per launch to get a payload into orbit. I predict, just as a really eyeballing the figures, I'm saying, like, if it costs $1 million an hour to run the space elevator, the SSTS, as I call it, because it has to have a boring acronym, right? The Segmented Space Transport System. It will cost. It will get to orbit about once every 4 hours. If it costs $1 million an hour to launch a payload, it will cost $4 million per launch, basically, per payload. So you can see already that it may well provide a substantial cost-benefit saving over rocket launches. And it will be a very useful machine if we can get stuff to low Earth orbit more easily. It will allow us to far more regularly get cargo up there. We can begin the process, for instance, of building the largest ships that we need to send astronauts, for instance, to Mars or to the outer solar system even one day, out to Jupiter, Saturn, Uranus, Neptune, to have astronauts one day landing on the icy moons of Jupiter. I think I want to live in that sort of world. I think most of us probably do. Certainly, I think most scientists and engineers want that sort of world. We don't want to be trapped on Earth forever, I don't think, and suffer the oblivion of using up all our natural resources and slowly fading away as a civilization. I think we want to go on to newer, higher pinnacles, as the great Walt Whitman poem Eidolons implies that we ought to do. And yes, I think so. Like the way the space elevator will work is it will be constructed in 3 stages. The first stage will be 120,000 feet high, going up to the end of the stratosphere more or less, utilizing turbofan jet engines to remove compressive stress from the structure, allowing us to build it out of more conventional materials, to some extent possibly steel, possibly a matrix of carbon fiber reinforced polymers also to save on weight and add steel for rigidity and things like this in a sort of a hybrid composite design. I'm still working through the research and development of the project on that level. I haven't entirely decided even on materials yet. What I do know, however, is that the concept works. The concept in theory works. That is the point. We don't know yet whether or not this works in practice. I suppose we will find that out in the course of this endeavour. And the timescale is by 2040 when I want it constructed. At the same time as Japan want to build their space elevator with the Obayashi Corporation. And yes, to utilise first of all the jet engine to remove compressive strain from the structure. Also lift balloons filled with helium to yet again remove further compressive strain from the structure and to cut down at our optimum on the amount of fuel that the structure will be using. Further up the structure up to sort of about 100 or 80,000 or 70,000 even to about 100,000 feet, we could be using ramjets and scramjets to further remove compressive strain from the structure. Above 100,000 feet, we would have to use turbojets, the same sort of jet engine that the SR-71 Blackbird uses. And up at that altitude, the lift balloons will eventually become redundant. They will become redundant at about 150,000 feet or so, and that is when they will really stop lifting anything. So after that point, we will have to stop using lift balloons. As for the second stage will be launched into space, so we will need a lot of rocket launches to launch the second stage into space. And I think you'll be able to see at this point how the project will be becoming progressively harder after the first stage. The first stage will be the most straightforward, but building up to 120,000 feet is not straightforward either. It will need to be steered and controlled by software, by AI basically steering it against the 120-mile-an-hour winds of the upper stratosphere, for example, steering it against every weather system we know about, connected to meteorology software so it can preserve itself during storms depending on where we place it on the planet, if we place it near the equator or in the continental United States or wherever this is going to end up. The equator is a good location, however there are more storms at the equator, so that is something we need to take into consideration. It might be advantageous, for instance, to build it on the plains of Texas, for example, where Starbase is located, because you've got these lack of storms and things like this. So it will, yes, building the second stage in space, so about 50 to 60 kilometers of segments, each using either rocket propulsion or ion thrusters to maintain it above the Kármán line. That stage will then dangle cable down through the mesosphere, where it will connect to the first stage. Then the third stage will be built in the mesosphere, which is, I suspect, by far the most challenging aspect of this project, and it will need to be built gradually with robots. What we can, however, do is use the second stage in space and the ion thrusters to provide thrust to remove compressive strain from the section in the mesosphere while the robots go along the cable building the third stage, the mesosphere stage, the stage from about 120,000 feet or so to 100 kilometers, like the Kármán line. That stage will need to integrate rocket propulsion in its operational matrix. Another idea I've had also is utilising the vertical winds of the mesosphere, these 150-mile-an-hour vertical winds, and using sails basically to instead of lift balloons, to provide yet more lift and to remove those requirements for fuel from the rocket engines that will also be supporting it. So it's up in the mesosphere, there is simply not enough oxygen to utilise jet engines, so we must use rocket propulsion. Rockets, this is hard. This is very, very hard. They burn at the same temperature as the surface of the sun, for goodness sake. They are liable to malfunction. They need to be as solid and as reliable, and it needs to be replaced as little as possible and to be serviced as little as possible, and to remain operational for as long as possible to further reduce the cost requirements per hour of this project. So yes, sails I think is a good idea. Luckily in the mesosphere there are vertical winds. So we've got these big convection currents, wind coming upwards, or hopefully we can utilise that to some extent. We need protection from things like micrometeorites, so we need the same sorts of panels that they use on the space shuttle, for example, that is kind of like with a gap there, so that the micrometeorite impacts and sort of breaks up and doesn't go through the second panel. This sort of stuff, built out of very tough materials, insulated with things like Kevlar, possibly even, and to eventually connect it all up and have an elevator going up to about 160,000 kilometers or so. What we could furthermore do is build a very large space station or docking station at the end of the space elevator to act as kind of an anchor for the whole thing, to just add a bit more pulling force on the whole structure to again relieve compressive strain on the structure and eliminate some of the requirements for fuel and things like this. And this brings me on to my next point, which is possibly the most difficult, one of the more difficult aspects of this, but not impossible, I don't think, how we will conduct fuel up this enormous tower that we're building to space. We will have to pump liquid oxygen and liquid hydrogen up there, for example. That will be very challenging, of course, keeping the hydrogen and oxygen at cryogenic temperatures while pumping it up the structure. Luckily it is rather cold up there, so that will eliminate some of the requirements for cooling and insulation. Then we're going to have pumps pumping it. Those pumps need to remain operational and not, for instance, freeze or be subjected to too many adverse weather events and things such as this. That's also something we need to consider. Then there's the conduction of, we probably want water being conducted up there for the various reasons that we need water in space for drinking water, possibly even, that sort of thing. We probably want electricity running up it, which that is not as nearly as challenging as the rest of it. Like, I'm sure if we can pump liquid oxygen and hydrogen up to 160 kilometers above Earth, we can most certainly get electricity up there. So that's pretty easy, I think, to do that. Other things to consider. Other things to consider. Well, I suppose the other things to consider, like the engineering merits of it. I think that this endeavour has a lot of merit in terms of what we'll learn about engineering, what we'll be capable to do after having built it. It opens up a world of possibilities of things we can do in space. It radically reduces the cost of rocket launches. $1 million an hour to run it makes it cost $8.6 billion a year to keep it operational, which, I mean, is a meaty fraction of NASA's budget. That's a fairly big chunk of NASA's budget, but it's not all of NASA's budget by any means. And I think NASA, for example, would appreciate the utility of building such a thing. I don't think that we should allow the West to decay. I think we should go on to be competitive on the global stage. We should be competing in the space race with India and China. Hopefully having friendly competition with them. And we should be, after all, the West, America, United States, North America, Europe, we've done the most in space currently. We've gotten the furthest. We've gotten people on the moon. We spearheaded the International Space Station, the development of that. And it would be a shame to fold when we've got really quite a good hand, if you see what I mean, to use a poker analogy. We've got sort of like a king and a 10 or something. And I think there's a king in the flop. But I'm stretching this analogy, So I think we should keep going. I really do. And I think this is probably the next step. Probably. A 36,000 kilometre space elevator to geostationary orbit is probably beyond us this century. It's probably not a particularly useful machine. It's probably a bit unnecessary, I think. But a 160 kilometre structure going up to low Earth orbit, they do say when you get to low Earth orbit, you're halfway to anywhere. And we will furthermore probably, we might still need rockets to get further out if we want to go out straight away, or if we want to go further out quickly on a rocket, for example. I don't think we should retire rockets, but the analogy I always draw, that the space elevator, or perhaps one day space elevators, will be sort of like the railroads to space. Cheaper to construct, cheaper to operate, and rockets will be sort of like the airlines and cargo planes, if you see what I mean. So my company, well, not official company yet, but my shadow corporation, Astrodyne Rocketjet, will be constructing the world's largest rockets, obviously, as well, with something called Operation Stratonimbus, which will be an endeavour in pushing rocket technology towards the limits imposed by the Tsiolkovsky rocket equation to about 200 metres tall or so, or that will be the objective, to see if we can build a rocket that large and get off the launch pad and into space. And launching very, very large rockets indeed. Rockets larger than some of the tallest skyscrapers in London. And to get the second stage into space. So where exactly do we go from here? I need to do this lecture at this conference in order to interest scientists and engineers in the project, interest the appropriate organisations, to gain funding for the research and development of it, for the teams of people I'd need to put together to model it completely with computers, to test it with computer animated design software, to figure out the appropriate means of figure out like exactly, for instance, how much it's going to cost, how much fuel it's going to use, how often it's going to need to be serviced. From the turbofans down at the lower stages to the scramjets, ramjets, and turbojets as we get higher, how often those rocket engines are going to need to be replaced, how much lift exactly the sails can provide, up at the mesosphere stage, how much ion thrust propellant we're going to need, how to get that up there, and ultimately, like how much it's going to cost to run. Because like a ballpark figure, I think, is $1 million an hour. If it is that, it is a very good saving over rocket launches. It might even be less than that. We don't know, I don't think. I suppose one of the bigger costs also will be staffing of the thing, and how much exactly we're going to need humanity to literally fix things themselves. Like for instance, how many aeronauts and astronauts we're going to need to go up there and say pressure suits, like in the film Ad Astra, frankly, and fix an antenna or like fix a bit on the thing that's broken, fixing a sensor or something like that. We need people climbing around on top of it one day, maybe. How much they're going to need to be paid, all things like that. Things like I can't really do on my own. So that will be, a challenge. So like, I'm going to wrap this up now because I think I've given a good enough overview of the entire project as it stands, where I'm at with it, and the concept that I'm working with, and I think on balance, like it is possible to do this. By 2040, I think it will certainly be possible. By 2040, I think someone will have done this. Obviously, we should get going on this really as soon as possible, trying to build the first stage, I think. Which would be a good test of the principles involved. If we could do the first stage, then we should just do the rest of it, I think. And get it operational as quickly as possible. And start building big ships up in space and have a docking station. And keep the rockets as well, because it's part of our traditions. It's part of our spacefaring heritage. And we love rockets, well, I love rockets. So it won't replace rockets, I don't think. If you want to get to the moon in a hurry, it might be a bit laborious to spend 4 hours getting on the space elevator, then getting in a ship and going to the moon. A rocket gets to space in minutes. It gets to the moon in a couple of days, with current propulsion technology. I don't know, it depends on how much cheaper that technology becomes in the future, I suppose. It might outcompete rockets, you never know. Rockets might become redundant, there's also that. But I think it will be some sort of analogy between airliners and trains, railroads. I think that's the analogy I'd like to draw. So, 36,000 kilometers long space elevator, just to summarize, a little bit pointless. Space elevator going up to LEO, low Earth orbit, quite a useful idea, I think. Something that a few people online are sort of talking about, I've discovered, but no one's really seeing the utility of it yet, which is a little bit disappointing in my opinion, since that is probably the direction we need to be going in to get a space elevator, a real space elevator, to be operational. Thank you for watching. Please leave your suggestions in the comments. Please like it if you liked it, and I hope to see you soon.